Assalamu alaikum. First of all, I want to thank the organization committee for the success of this international conference. Uh, I want to start this presentation by presenting myself. My name is Larbaoui Ahmed. I'm a teacher at Mascara University, Mustafa Stambuli, Electrical Engineering Department. I am honored to be here today to present you the essential of my work entitled Comparison between PI and Fuzzy PI controllers for DC-DC multi-level boost converter. So, the fast growth of power electronic equipment and devices operating separately or in combination to convert electric energy efficiently made power electronics to be more applicable in broad areas compared to another engineering field. During this era, power electronic control technologies need to utilize power conversion control strategy to convert energy from one source to another. According to the World Global Energy System, the current years the world is experiencing electrical power crisis as a result of higher demand of energy consumption. This is caused by the fast diminution of fossil fuel-cited convection power supply systems and the rapid increase of electrical energy-based technology advancement. Even though a lot of power converters have been developed, still an improvement is required in the existing converters due to the low efficiency, high cost, low switching frequency, and low voltage gain. For example, renewable energies like PV system, wind turbine, and fuel cell generating low voltage need a high voltage converted device before inverting to AC source connected to the main grid of the system. So the multi-level DC-DC converter is proposed in this work, and some of this topology, the DC-DC multi-level converter presents advantages like low harmonic distortion, low voltage stress, low EMI or electromagnetic interference noise, low switching frequency, high efficiency, and the ability of operating without magnetic components. So the plan of this presentation is as follow. I want to start this presentation by presenting the physical model of the multi-level boost converter, and then the mathematical modeling of the multi-level boost converter, and then the control of the DC-DC multi-level boost converter, and then the simulation results and discussion, and then the test of the robustness. And I want to conclude this presentation by so before passing to the physical model of the multi-level boost converter, the proposed multi-level DC-DC boost converter is DC-DC converter based on pulse width modulation (PWM) that uses a conventional DC-DC converter and voltage switch capacitor to generate various voltage levels in the output using only a single switch, 2n-1 diode, one inductor, and 2n-1 capacitor for the n-time MBC. This converter is used as a DC link in various applications such as photovoltaic system or fuel cells that need multiple regulated voltage levels with continuous and unidirectional current flow and self-balanced voltage for grid-connected AC inverters and HVDC distribution system. So let us consider the electrical diagram in figure 1 that depicts two-level DC-DC boost converter. It consists of a solar cell as DC input voltage source VG, a controllable switch, a filter inductor L, a filter capacitor C1 and C2, a load resistor R, and a PWM block. It is clear that for this particular converter, the number n is equal to 2. In the subsection, V3 is a notation related to voltage across a capacitor that is not at the output of the MBC. So the mathematical modeling of the multi-level based boost converter. This image shows equivalent circuits for 2 MBC when the switch is closed. That is, this is delta equal to 1. So the equation 1 represents the dynamic related to inductor and the n+1 capacitors of the 2 MBC when the switch is closed. So this is the equation 1 and the equation 2. Figure 3 shows the equivalent circuits for the 2 MBC when the switch is open, that is delta equal to 0. Equation 2 represents the dynamic related to the inductor, the equation 2 which is shown in the previous slide. So represent the dynamics related to the inductor and the n plus 1 capacitors of the 2 MBC when the switch is opened. So the general model, the average output voltage equation of the multi-level boost converter is given by the equation 5. From this equation, the average dynamic model of the multi-level boost converter can be written as the equation 6. The small signal modeling. In each configuration, the system can be represented by general model 6, the equation, the previous equation, and in the form of the equation of state, the equation 7, where T is the vector of the state variables, the current and the voltage. The average large signal model does not imperatively to establish a model for the control by techniques of linear automatic system. Since the product between the control variable delta and the state variable, the current and the voltage writing of the transfer function is not possible. In contrast, the small signal modeling allows linear representation. This leads to the construction of a model, small signal. Now, consider a converter having two sequences of operation. We can get the average state model as follow the equation 8. The Laplace transform, we can obtain the expression of the transfer function as the equation 10. Now we present the control of the DC-DC multi-level boost converter. The PI controller, which its control strategy comprises two control loops, as shown in this image. The inner loop, which is the current control loop, which is a fast loop, and the outer loop, the voltage control loop, which is a slow loop. The current loop design is shown in this figure, and the current loop transfer function from the equation 10 is given by the equation 11. And the outer voltage control loop is shown in this image, which generates the inductor current reference, IL reference, for the inner current control loop. And from the equation 16, the transfer function of the voltage loop is given by the equation 12. Now we present the fuzzy proportional integral control system. The fuzzy PI controller is shown in this image, uses the error signal E and its derivative DE from the measured data, pre-processing step as input. If the output signal describes the necessary difference toward the current output value, you need a subsequent integrator device to build up the command variable value. Fuzzy logic provides the solution for controlling nonlinear processes, and it can handle ambiguous and uncertain situations. Fuzzy control is derived from fuzzy set theory. The fuzzy control for the chosen converter is developed using input membership function for error E and change in error DE, and the output membership function for the current of the inductor of the DC-DC boost converter is given by the next equation, where the IL reference is the reference of the desired output current and the IL is the actual output current. To convert these numerical variables into linguistic variables, the following 7 fuzzy levels or sets are chosen as NB negative big, NM negative medium, NS negative small, ZE 0, PS positive small, PM positive medium, and PB positive big, as shown in. So before presenting the simulation results, we discuss the simulation model, which is two MBCs that are governed by state space averaging technique, which was implemented in simulating block diagrams. The element of the matrices are evaluated by the value given in the previous table. The load resistance value has been modified in this simulation work so that the output can be analyzed to ensure whether the variation of load affects the output in terms of overshoot, rise time, and settling time. So the first figure shows the output voltage, which reaches the expected value of 48 volt, higher than the input value 12 volt, with a constant duty cycle of 0.5 For conventional PI, high overshoot occurred at the beginning of the simulation and ripple on the response, but for the fuzzy PI controller is satisfactory, less than 5%, and the absence of ripple, which is shown also in the second figure of the inductor current ripple. And for the test of the robustness, the load resistance value has been varied in this test so that the output can be analyzed to ensure whether the variation of load affects the output. So the first two figures show the output voltage and the current through the inductor under feedback control. The output voltage of the two MBC for different load with stepped up to 48 volt, it can be seen that there is no ripple and less overshoot in fuzzy PI controller system counterpart of the conventional PI controller. And for the current through the inductor, it is noticed that varies from it is noticed that it's varied from 100 milliampere to 230 milliampere with the change in loads. For the PI controller, a higher overshoot occurred and the presence of ripple, but for the fuzzy PI controller, it is occurred a good dynamic of response with the reducing of overshoot and absence of ripple. So the performance of the system has been improved using the fuzzy PI logic controller. And now we have reached the conclusion of this work. In this work, a two multi-level DC-DC boost converter operation has been analyzed using state space averaging techniques. Results of simulation and examples were presented to the MBC to illustrate the control strategy. Simulated results of the two MBC using conventional PI and fuzzy PI controllers shows that the corresponding change in the load resistance affect the output voltage and inductor current of the converters. Results show that the peak overshoot and the ripple are high in case of conventional PI controller. In order to overcome this issue, a fuzzy logic PI controller is used to form a closed loop control system using the desired performance, and the desired performance has been achieved. And thanks for your attention. Any questions?